We start then by considering A, which again we said is typical of normal operation as a motor. And so normally we would consider clockwise to be positive. Okay, so the magnetic field speed is ns, and if it turns clockwise, we have positive 1200. And the rotor speed is n, and if it is also clockwise, 1150 RPM. And so we have, a difference in speeds here of 50 RPM, and we will consider that to be the slip speed, unless we're asked specifically to calculate slip speed or slip in RPMs. We should believe that we're expected to calculate slip as a percent. And so as a percent, slip is equal to ns minus n divided by ns, and remember then times 100 to convert that decimal to a percent. And so that gives us 1200 minus 1150 divided by 1200, which of course is 50 divided by 1200. Now I'll omit the times 100%, but don't forget that you got to do it. And so slip then he does the calculation, comes up with a decimal of 0.041666 repeating. He multiplies that by 100 and rounds. Don't forget to round it up, right? So you should be telling it in 4.17%. And again, we'll say that that represents normal full load operation of a motor, somewhere close to that value. Okay, so for part B then, we got to be thinking that normally the rotor does not go faster than the speed of the field or the sync speed. And so, again, we'll point out that that's not normal or typical operation of a motor. So something's going on there, right? And again, it could be generator action, or it could be a variable speed drive that's in the process of slowing the motor down by reducing the frequency. In any event, we can calculate the slip. And so ns is the field speed, and well, we're saying that hasn't changed. But of course, if a variable speed drive is in play, the field speed is what changes, and that affects rotor speeds. And so n, if it's all still clockwise, they're both still positive numbers, but n now be 1500. And so if we go ahead now and calculate the slip as ns minus n divided by ns, and so don't forget the 100%, right? This time we're going to have 1200 subtract 1500, and so you can see that numerator is going to be a negative number, divided by 1200, and so we have negative 300 RPMs divided by 1200 RPMs times 100%. And so that gives us a slip of negative 25%. And again, we stress that don't usually get that. But if the rotor could turn faster than the field, the slip would certainly be negative. Okay, part C then Again, we're not considering that the field speed is changing here, but we know that for braking action, for variable frequency, we would consider that to be the case. Now this time, we're saying that the rotor has been reversed. If it's going counterclockwise, we're saying negative 1150 RPM. And again, if the field was moving counterclockwise and the motor was spinning counterclockwise, and all of a sudden a phase change meant the field reversed to a clockwise direction, that would, be what's going on here, possibly. And the idea is that, we normally take clockwise as positive, and so therefore in would be negative in this case. And so now the slip would be 1200 subtract negative 1150. And so you can see, I guess, that numerator now is going to be bigger than the denominator. And so that means that we're getting a number bigger than 100%. And so we end up with, on the top, 2350. On the bottom, 1200. And if we work that out and round to true significant digits, 196%. And so again, not normal operation as a motor. And so we'd have to conclude that something is going on there. And again, the most likely scenario for that one is reversal or electromechanical braking.